I don't know how many of you are familiar with the cassava plant, which is a kind of woody shrub that's first been cultivated in South America, but it's grown throughout Africa, the Caribbean, South America still, many places around the world. And this is a major source of carbohydrates for much of the world because the cassava root is very, very, very rich in carbohydrates. It's not the best form of food in that they're actually very poor in protein and unfortunately very, very rich in cyanide. So these roots can be very dangerous. There's different types of the root that you can get called the bitter and the sweet. Hopefully you would all choose the sweet if two are put in front of you. The bitter, of course, are the ones that are very high in cyanide. If you eat these raw, which they do in many places around the world, if you eat a bitter one, you could, in fact, get enough cyanide to kill you. And there are ways to prepare these, so it's important. This is kind of thinking of more along the food science idea. There's a way to actually grind down and prepare the flour so that you promote the enzymes within the plant to break down the cyanide precursors. And if you put this in a well-ventilated area, if you prepare this outside, the HCN gas will actually be released into the air, so you're safe. You can eat it later. About 80% of the cyanide at that point is gone. So it does render the root much more safe, but you do, in fact, have to worry about long-term exposure, cyanide poisoning in terms of long-term effects in certain populations that do get the bulk of their carbohydrates from this root, from the root of the cassava plant. But in terms of us going to the grocery store and thinking about things, probably we're all breathing sighs of relief. I just told you almonds are not a problem, no worries there. We probably don't find any forms of the cassava plant ever in the US that are going to have that high cyanide content, so we should all be relieved. Unless, of course, you're a smoker or you're thinking of becoming a smoker, and then maybe you should worry because this is one of the advertisements that was airing in terms of the anti-smoking campaign. Hydrogen cyanide is found in cigarettes. So if you're looking for another reason to quit, if you're looking for a reason not to start smoking, here's another good one. As I said, it's a particularly hazardous substance. This is worked with in fume hoods. You don't want to inhale it. It's definitely not recommended. The way, in the simplest terms, that cyanide can kill you is it basically outcompetes your oxygen for the heme in your blood. So instead of carrying oxygen to your cells, you're carrying cyanide to your cells. You know, obviously, the amounts that are in cigarettes are not enough that people are dropping dead of cyanide poisoning, but still, it's not a good idea. If you can avoid eating or inhaling cyanide, you definitely want to minimize your exposure. And in terms of thinking about it for organic chemistry, or if you're interested in thinking about the mechanism maybe by which it is toxic, a first step would be to draw its Lewis structure. So let's go ahead and make sure we can draw that if we have interests either in the area of organic chemistry or biochemistry or biology here. So in terms of the first step of the skeletal structure, this is actually going to be easier because we don't have a central atom. We just have carbon and nitrogen here. Our next step is thinking about valence electrons. So we have 4 plus 5. But we're actually not done yet because it's Cn minus. So if we have minus, we actually have an extra electron in our molecule. So we need to add one more. If instead we had a positive ion, a cation, what we would have to do is subtract 1. But here we're going to add 1. So again, we have 10 valence electrons. And if we go on to step 3, where we figure out how many we would need for full octets, it's just going to be 2 times 8. So we have 16. And step 4 is going to have us figure out how many bonding electrons we have. So we have 16 minus 10 is going to be 6 bonding electrons. So step 5 tells us to add 2 electrons between each atom. So we add 2 there. And step 6 asks us, well, do we have any bonding electrons left? So how many bonding electrons do we have left? Yep, so we do. We have 4 left. We started with 6. We only used 2. This is a very easy molecule because we know exactly where to put them without even having to think. We only have one option. And we'll make a triple bond between the carbon and the nitrogen.